Hello grade 11s. In grade 10, you learned about scalar quantities and vector quantities. Examples of scalar quantities are distance, speed, and mass. Then there are vector quantities that have both magnitude and direction. In other words, we need two pieces of information to describe them. If we talk about any of these quantities, we have to ask, how big is it, and in what direction is it acting? Examples of vector quantities are displacement, velocity, and weight. Here, I'm holding a brick. It has a mass of 2 kilograms, but what I experience in my arm is weight, which is a force of 20 newtons and it acts in a downwards direction. So weight is a vector quantity because it has a magnitude of 20 newtons in this case and a direction which is downwards. In grade 10, you dealt with vectors in one dimension. That is, the vectors always acted along the same line. In grade 11, we deal with vectors in two dimensions. Imagine you are the skipper of a fishing boat on the wide open sea. You have to reach a particular island on the map. The map shows that the island is 100 kilometers northeast from where you are. So your journey is made up of some displacement in the northerly direction and some displacement in the easterly direction. That's displacement in two dimensions. You can travel fast, but your direction is also important. The boat has a compass that shows whether the boat is going north or northeast or east. The boat's movement has both speed and direction, and so we call the movement a vector quantity. Now I will introduce you to Shanti, who will take you through a problem. A man called Ishmael needs to get his boatload of school children across a river.
Hi, and welcome to another lesson on working with vectors. In this lesson, we will be examining practical situations that involve movement. Can you recall how we defined velocity? Velocity is the rate of change of displacement. And remember too, that the velocity is a vector and is different to speed, which is a scalar. When we add velocity vectors together, we will need to use the rules of vector addition. In this lesson, we consider situations where two different velocities result in the motion of an object. In this lesson, let us tackle problems of how to get across a river. Consider a problem in which a river flows to the east at 3 meters per second. A boat moves through the water at 4 meters per second. Every day, Ahab crosses this river in his boat to take his children to school. He has crossed this river nearly every day of his life. He can do it with his eyes closed. He is doing what his father taught him and his father before that. Without him even knowing it, he is working scientific formulae in his head. You and I would have to give this crossing some serious consideration. One day, Ahab gets sick, and his friend Ishmael promises to take the children to school. It was a disaster. Ishmael found himself drifting towards a crocodile. What do you think happened? Ishmael is situated at point A on the riverbank and needs to cross over to point B on the other side of the river. Point B is exactly due north of point A. In other words, he wants to go due north across the river. Without their dad, I am certain these children will be late for school. Why? Well, this is what happened. They set out heading north at 4 meters per second. After 1 second, they had moved forward by 4 meters in a northerly direction. But the current has carried them downstream for 3 meters in an easterly direction. As they drift downstream, they begin to make an angle to the riverbank. After 10 seconds, they have moved forward 40 meters due north, but they have been carried 30 meters downstream. With a crocodile resting downstream, will the children get safely across the river? The children are well off course, but they do reach point C, which is 300 meters downstream from point B, well clear of the crocodile. The river has been carrying them downstream at a rate of 3 meters per second. Seeing as the children have never been late before, we need to find out how late they were getting to school. Let's draw a displacement diagram of the children's journey showing all the facts. They started at point A and arrived at point C, so their displacement is from A to C. We can work out how late they were by using the relationship between the average velocity, the displacement, and the time. The average velocity is equal to displacement divided by the time taken. And by changing the subject of the formula, we can calculate the time taken, which is equal to displacement divided by the average velocity. Now we need to be very careful when using this formula that relates average velocity and displacement to time. We must make sure that the displacement and velocity vectors act in the same direction. Let's look at our problem again. We need to find the time taken for the boat to cross the river from point A to point C. But we do not know this displacement or this velocity yet, so we can't do this directly. Now, is there a pair of velocity and displacement vectors that act in the same direction that we do know? That's right, we know the displacement from B to C. So displacement BC and average velocity BC in this direction here. The displacement is 300 meters that he drifted downstream divided by the average velocity of the river current that carried him 3 meters per second. So the time taken is 100 seconds to travel 300 meters downstream. Now let's substitute the values into this equation. We are given the displacement that he drifted downstream as 300 meters. And we are told that the current in the river carried him downstream as 3 meters per second. So the answer to the time taken is 100 seconds. So he took 100 seconds to drift 300 meters. Clearly, this is also the time it took him to cross the river. Now, can you use the given information to work out how wide the river is? The displacement of the boat from A to B is also the width of the river. The velocity of the boat without the current is 4 meters per second in a northerly direction. Now, it is this velocity that is in the same direction as the displacement AB. What else do we know? We know that the time taken to cross the river is 100 seconds and that there is a formula that relates average velocity, displacement, and time. But we can only use this formula when the direction of the vectors are the same. The average velocity AB is equal to the displacement AB divided by the time taken. Now, changing our formula and making displacement AB the subject, we have displacement AB is equal to the average velocity AB multiplied by the time taken. We know that it takes Ismail 100 seconds to travel from A to C on the other side. And we know that the boat travels at 4 meters per second. Now we can substitute these values into the formula. So we have the average velocity as 4 meters per second multiplied by the time, which is 100 seconds. We find that the width of the river is 400 meters. Let's try another question about Ismail's journey. What is Ismail's displacement from his starting point? We can use the theorem of Pythagoras to calculate the magnitude of the displacement. So S squared is equal to 300 meters squared plus 400 meters squared. Therefore, S is equal to the square root of 300 meters squared plus 400 meters squared. Using your calculator, you will find that S is equal to 500 meters. And now we must determine the direction in which Ismail and the children moved. The direction from A to B is due north. So we will be using trig ratios to calculate the direction relative to this line. So the tan of angle theta is equal to 300 meters divided by 400 meters. So using your calculator, theta is equal to 37 degrees. So Ismail's displacement is 500 meters at an angle of 37 degrees east of north. Before we move on, let us look at our vector diagrams again. Notice that we have used displacement values in this diagram. There are two other points to note. We never mix displacement and velocities in the same diagram. When calculating, we must use the displacement and velocities that are in the same direction. So we can now consider one more question. What is Ismail's resultant velocity? Do you remember what a resultant is? A resultant is the sum of two or more vectors. Here is the velocity vector diagram. There is the velocity of the water down the river. Then there is the velocity of the boat due north across the river. And finally, this line represents the resultant velocity of the boat. We can use the theorem of Pythagoras to calculate the magnitude of the resultant velocity. The yellow line is the resultant velocity, which we will call v. And v can be calculated as a square root of 3 meters per second squared plus 4 meters per second squared. And using our calculator, we find the answer as 5 meters per second. And now we will apply trig to find the angle theta. So tan theta is equal to 3 meters per second divided by 4 meters per second. Using your calculator, you find that theta is equal to 37 degrees. So the resultant velocity is 5 meters per second at 37 degrees. In our next lesson, we will return to this problem in order to label these velocity vectors more accurately. Do you notice that both the yellow and the black vector are the velocity of the boat? The only difference is that the yellow vector is the resultant velocity. How can we label this black vector more accurately? Well, that's a problem for our next lesson when we will introduce you to a new idea called relative motion. Now it's time for today's task. In this problem of crossing a river, the boat took 100 seconds to move from A to C. If there was no current, how long would the boat take to cross the river if Ismail moved with the same velocity of 4 meters per second? But before we end today's lesson, let me emphasize an important point that you must remember. When we drew a displacement vector diagram on which we marked the positions A, B and C along the river bank, and we marked in some displacement vectors too, this diagram never showed anything that referred to velocity. The important point of today's lesson is that a displacement vector diagram deals only with displacements, and a velocity vector diagram deals with velocity. Always keep these diagrams separate from each other.
Thank you, Shati, for that lesson. Now let's try the problem she set. The boat took 100 seconds to move from A to C. If there was no current, how long would the boat take to cross the river if Ismail moved the boat with the same velocity of 4 meters per second? Did you get the answer of 100 seconds? Let's see what you had to do. What was the width of the river? What was the speed of the boat? Remember that there was no current, so the boat was not being dragged eastwards while it was going northwards. So the boat covered the 400 meters at a rate of 4 meters in each second. How many times does 4 meters per second divide into 400 meters? In this lesson, you used Pythagoras' theorem and your knowledge of trigonometry to calculate the resultant velocity, its magnitude, and its direction. And that's all for this lesson. Don't forget to check out other videos in this series, especially the task video. Also look at the Mindset website at www.mindset.co.za/learn. Goodbye.